Hey there, science fans. Welcome to another exciting journey into the world of molecules and atoms. Ever wonder why molecules have different shapes? It's a fascinating question that takes us deep into the heart of chemistry. It's like building with tiny blocks, but instead of blocks, we have atoms. Just like how kids build castles and towers with their blocks, scientists build molecules with atoms. VSEPR theory helps us understand this. It's a key concept in chemistry that explains why molecules take on the shapes they do. VSEPR stands for valence shell electron pair repulsion. It might sound complicated, but it's actually quite intuitive once you get the hang of it. Don't worry about the long name, it's simpler than it sounds. Think of it as a way to predict how atoms will arrange themselves in a molecule. Imagine atoms are like building blocks and electrons are the construction crew. The electrons move around and arrange the atoms in the most stable configuration. The way these electrons arrange themselves determines the final shape of our molecule. Just like the placement of blocks determines the shape of a building. The electrons repel each other and settle into positions that minimize this repulsion. This is the basic idea behind VSEPR theory. It helps us predict the three-dimensional shapes of molecules, which is crucial for understanding their properties and behavior. VSEPR theory helps us predict these molecular shapes by focusing on electron pairs in the outermost shell of an atom. These pairs of electrons are like the architects of the molecule. Why the outermost shell? Because that's where all the action happens. It's where bonds are made. The electrons in this shell are the ones involved in chemical reactions and bonding, making them crucial for determining the shape and stability of the molecule. Remember those electrons, the construction crew of our molecular building? They're negatively charged particles, and like tiny magnets, they want to be as far apart from each other as possible. This is key to understanding VSEPR theory. There are two main types of electron pairs: bonding pairs and lone pairs. Bonding pairs are like the glue that holds two atoms together in a molecule. They are shared between two atoms, forming a strong bond. Lone pairs, on the other hand, are like the lone wolf of electrons. They belong to a single atom and aren't involved in bonding. But don't underestimate them. They play a crucial role in determining molecular shape. Now here's where things get interesting. Remember how electrons want to be as far apart as possible? Well, electron pairs feel the same way. Whether they're bonding pairs or lone pairs, they repel each other. This repulsion is strongest between two lone pairs because they're hogging all the space around a single atom. The repulsion is weaker between a lone pair and a bonding pair, and weakest between two bonding pairs. Think of it like this. Lone pairs are like two grumpy people sharing a small room. They want to be as far apart as possible. This electron pair repulsion is the driving force behind VSEPR theory. It's what pushes and pulls the atoms in a molecule into their final shape. The molecule will settle into a geometry that minimizes this repulsion, giving everyone enough space. Imagine you tie a bunch of balloons together. What happens? They naturally spread out, right? That's because the air inside each balloon is pushing against the others. It's the same with electrons. The more electron pairs there are around a central atom, the more they'll repel each other, and the further apart the atoms will be pushed. This leads to different molecular geometries, or shapes. Section 5. Linear and trigonal planar, simple shapes. In this section, we will delve into the fundamental molecular geometries that form the basis of more complex structures. Let's start with the simplest molecular shapes. These basic shapes are crucial for understanding how molecules interact and form more intricate patterns. When a central atom has only two bonding pairs and no lone pairs, like in carbon dioxide, the molecule takes on a linear shape. This linear configuration is one of the most straightforward molecular geometries. The two oxygen atoms are positioned on opposite sides of the carbon atom, forming a straight line. This arrangement minimizes repulsion between the electron pairs, resulting in a stable structure. With three bonding pairs and no lone pairs, we get a trigonal planar shape. This shape is equally important and is often seen in molecules with three substituents. Imagine a flat triangle, like a slice of pizza. This visual can help you understand the spatial arrangement of atoms in a trigonal planar molecule. Boron trifluoride is a good example, with the boron atom in the center and the 3 fluorine atoms at the corners of the triangle. This arrangement allows for equal spacing between the atoms, reducing electron pair repulsion. These are just 2 basic examples, but there are many more shapes, each determined by the number of bonding pairs and lone pairs around the central atom. Let's explore some more. Understanding these shapes is fundamental to grasping the complexities of molecular geometry and how molecules interact in various chemical reactions. Section 6. Tetrahedral and trigonal, bipyramidal, getting complex. Things get even more interesting with 4 electron pairs. With 4 bonding pairs and no lone pairs, the molecule takes on a tetrahedral shape. Picture a pyramid with a triangular base. That's a tetrahedron. Methane is a classic example, with the carbon atom at the center and the 4 hydrogen atoms at the corners. With 5 electron pairs, things get even more complex. We enter the world of the trigonal bipyramidal shape. Imagine 2 pyramids stuck together at their bases. Phosphorus pentachloride is a good example, with the phosphorus atom at the center and the 5 chlorine atoms at the corners. It's like building a more elaborate structure with our molecular blocks, isn't it? But wait, there's one more shape to discover. Section 7. Octahedral, the 8-sided wonder. Hold on to your hats because we're going to the next level. With 6 electron pairs, we encounter the majestic octahedral shape. Imagine a shape with 8 faces. That's an octahedron. Sulfur hexafluoride, or SF6, is a prime example, with the sulfur atom at the center and the 6 fluorine atoms at the corners. So, we've gone from simple linear shapes to complex octahedrons, all thanks to the power of electron pair repulsion. But we're not done yet. Remember those lone pairs? They have a few tricks up their sleeves when it comes to molecular shapes. Section 8. Lone pairs, the shapeshifters. Lone pairs don't form bonds, but they still take up space and repel other electron pairs. This means they can actually distort the ideal molecular geometries we've discussed. For example, water, H2O, has 2 bonding pairs and 2 lone pairs around the oxygen atom. This would normally suggest a tetrahedral shape. However, the lone pairs, with their stronger repulsion, squeeze the bonding pairs closer together, resulting in a bent or V shape. Lone pairs are like those sneaky friends who always manage to change the plans. They add an element of surprise and complexity to the world of molecular shapes. Section 9. Geometry in action, from water to DNA. In this section, we delve into the fascinating world of molecular geometry and its profound impact on the natural world. Understanding molecular shapes is not just an academic exercise. It's crucial for understanding the properties and behavior of substances in the real world. These shapes dictate how molecules interact with each other, influencing everything from chemical reactions to biological processes. For example, the bent shape of the water molecule is responsible for its polarity, which explains why water is such a good solvent. This polarity allows water to dissolve a wide variety of substances, making it essential for life as we know it. The double helix structure of DNA, the blueprint of life, is also a result of specific molecular geometries. This iconic shape is not just for show, it plays a critical role in the replication and function of genetic material. The interactions between the base pairs are influenced by their shapes, ensuring the genetic code is passed on accurately. These precise interactions are what allow DNA to store and transmit genetic information with high fidelity. From the air we breathe to the medicines we take, molecular shapes play a vital role in our everyday lives. The geometry of molecules affects how pollutants interact with our environment and how drugs interact with our bodies. So, next time you encounter a molecule, take a moment to appreciate its unique shape and the underlying forces that determine it. These shapes are the result of complex interactions and are fundamental to the behavior of all matter. Section 10. Molecular Shapes, a World of Possibilities. So there you have it, the fascinating world of VSEPR theory. We've seen how electron pairs, like tiny architects, shape the molecules around us. From simple linear molecules to complex octahedrons, each shape tells a story about the arrangement of electrons within. Remember, understanding molecular shapes is key to unlocking the secrets of chemistry and beyond. It helps us understand the properties of substances, predict their reactions, and even design new materials with specific functions. So keep exploring, keep questioning, and never stop being curious about the invisible world of molecules that make up our universe.